fact. But then, who gives us the right of attributing to the principle itself more generality and more precision than to the experiments which have served to demonstrate it? This is asking if it is legitimate to generalize, as we do every day, empirical data, and I shall not be so foolhardy as to discuss this question, after so many philosophers have vainly tried to solve it. One thing alone is certain: if this permission were refused to us, science would not exist. Or at least it would be reduced to a kind of inventory, to the ascertaining of isolated facts. It would no longer be to us of any value, since it could not satisfy our need of order and harmony, and because it would be at the same time incapable of prediction. As the circumstances which have preceded any fact whatever will never again, in all probability, be simultaneously reproduced, we already require a first generalization to predict whether the fact will be renewed as soon as the least of these circumstances is changed. But every proposition may be generalized in an infinite number of ways. Among all possible generalizations we must choose, and we cannot but choose, the simplest. We are therefore led to adopt the same course as if a simple law were, other things being equal, more probable than a complex law. A century ago it was frankly confessed and proclaimed abroad that nature loves simplicity, but nature has proved the contrary since then on more than one occasion. We no longer confess this tendency, and we only keep of it what is indispensable, so that science may not become impossible. In formulating a general, simple, and formal law, based on a comparatively small number of not altogether consistent experiments, we have only obeyed a necessity from which the human mind cannot free itself. But there is something more, and that is why I dwell on this topic. No one doubts that Mayer's principle is not called upon to survive all the particular laws from which it was deduced, in the same way that Newton's law has survived the laws of Kepler from which it was derived, and which are no longer anything but approximations, if we take perturbations into account. Now, why does this principle thus occupy a kind of privileged position among physical laws? There are many reasons for that. At the outset, we think that we cannot reject it, or even doubt its absolute rigor, without admitting the possibility of perpetual motion. We certainly feel distrust at such a prospect, and we believe ourselves less rash in affirming it than in denying it. That, perhaps, is not quite accurate. The impossibility of perpetual motion only implies the conservation of energy for reversible phenomena. The imposing simplicity of Mayer's principle equally contributes to strengthen our faith. In a law immediately deduced from experiments, such as Mariott's law, this simplicity would rather appear to us a reason for distrust, but here this is no longer the case. We take elements which at the first glance are unconnected. These arrange themselves in an unexpected order, and form a harmonious whole. We cannot believe that this unexpected harmony is a mere result of chance. Our conquest appears to be valuable to us in proportion to the efforts it has cost, and we feel the more certain of having snatched its true secret from nature in proportion as nature has appeared more jealous of our attempts to discover it. But these are only small reasons. Before we raise Mayer's law to the dignity of an absolute principle, a deeper discussion is necessary. But if we embark on this discussion, we see that this absolute principle is not even easy to enunciate. In every particular case, we clearly see what energy is, and we can give it at least a provisory definition, but it is impossible to find a general definition of it. If we wish to enunciate the principle in all its generality, and apply it to the universe, we see it vanish, so to speak, and nothing is left but this: there is something which remains constant. But has this a meaning? In the determinist hypothesis, the state of the universe is determined by an extremely large number n of parameters, which I shall call x1, x2, x3, and so on to xn. As soon as we know at a given moment the values of these n parameters, we also know their derivatives with respect to time, and we can therefore calculate the values of these same parameters at an anterior or ulterior moment. In other words, these n parameters specify n differential equations of the first order. These equations have n-1 integrals, and therefore there is n-1 functions of x1, x2, x3, etc. to xn, which remain constant. If we say, then, there is something which remains constant, we are only enunciating a tautology. We would be even embarrassed to decide which among our integrals is that which should retain the name of energy. Besides, it is not in this sense that Mayer's principle is understood when it is applied to a limited system. We admit, then, that p of our n parameters vary independently, so that we have only n minus p relations, generally linear, between our n parameters and their derivatives. Suppose, for the sake of simplicity, that the sum of the work done by the external forces is zero, as well as that of all the quantities of heat given off from the interior. What will then be the meaning of our principle? There is a combination of these n minus p relations of which the first member is an exact differential, and then this differential vanishing in virtue of our n minus p relations, its integral is a constant, and it is this integral that we call energy. But how can it be that there are several parameters whose variations are independent? That can only take place in the case of external forces, although we have supposed, for the sake of simplicity, that the algebraic sum of all the work done by these forces has vanished. If, in fact, the system were completely isolated from all external action, the values of our n parameters at any given moment would suffice to determine the state of the system at any ulterior moment whatever, provided that we still clung to the determinist hypothesis. We should therefore fall back on the same difficulty as before. If the future state of the system is not entirely determined by its present state, it is because it further depends on the state of bodies external to the system. But then, is it likely that there exist among the parameters x, which define the state of the system of equations, independent of this state of the external bodies? And if, in certain cases, we think we can find them, is it not only because of our ignorance, and because the influence of these bodies is too weak for our experiment to be able to detect it? If the system is not regarded as completely isolated, it is probable that the rigorously exact expression of its internal energy will depend upon the state of the external bodies. Again, I have supposed above that the sum of all the external work is zero, and if we wish to be free from this rather artificial restriction, the enunciation becomes still more difficult. To formulate Mayer's principle by giving it an absolute meaning, we must extend it to the whole universe, and then we find ourselves face to face with the very difficulty we have endeavored to avoid. To sum up, and to use ordinary language, the law of the conservation of energy can have only one significance, because there is in it a property common to all possible properties, but in the determinist hypothesis there is only one possible, and then the law has no meaning. In the indeterminist hypothesis, on the other hand, it would have a meaning even if we wished to regard it in an absolute sense. It would appear as a limitation imposed on freedom. But this word warns me that I am wandering from the subject, and that I am leaving the domain of mathematics and physics. I check myself, therefore, and I wish to retain only one impression of the whole of this discussion, and that is, that Mayer's law is a form subtle enough for us to be able to put into it almost anything we like. I do not mean by that it corresponds to no objective reality, no, that it is reduced to mere tautology, since in each particular case, and provided we do not wish to extend it to the absolute, it has a perfectly clear meaning. This subtlety is a reason for believing that it will last long, and as, on the other hand, it will only disappear to be blended in a higher harmony, we may work with confidence and utilize it, certain beforehand that our work will not be lost. Almost everything that I have just said applies to the principle of Clausius. What distinguishes it is that it is expressed by an inequality. It will be said, perhaps, that it is the same with all physical laws, since their precision is always limited by errors of observation. But they at least claim to be first approximations, and we hope to replace them little by more exact laws. If, on the other hand, the principle of Clausius reduces to an inequality, this is not caused by the imperfection of our means of observation, but by the very nature of the question. General conclusions on Part 3. The principles of mechanics are therefore presented to us under two different aspects. On the one hand, there are truths founded on experiment, and verified approximately as far as almost isolated systems are concerned. On the other hand, there are postulates applicable to the whole of the universe and regarded as rigorously true. If these postulates possess a generality and a certainty which falsify the experimental truths from which they were deduced, it is because they reduce in final analysis to a simple convention that we have a right to make, because we are certain beforehand that no experiment can contradict it. This convention, however, is not absolutely arbitrary. It is not the child of our caprice. We admit it because certain experiments have shown us that it will be convenient, and thus is explained how experiment has built up the principles of mechanics, and why, moreover, it cannot reverse them. Take a comparison with geometry. The fundamental propositions of geometry, for instance Euclid's postulate,